Okay, so good to see you all. Today we are going over Lab 4. I hope you've been well this past week since I've last seen you. So we're going over human population growth and the exponential growth equation. Just bouncing off of what we went over last week about exponential growth models. We're now looking more specifically on how to use the equation, the different variables involved, and then looking more into that. So first, an outline for today's lab. We are going over our water resources data collection, so lab 5A, just a brief intro on what you would have to do after this lab ends. So you're going to be recording your own data, like your water use for the next 7 days, the next week before we meet for next week's lab for lab 5, because we're going to be using that data to look more specifically at what does your water use look like in comparison to the average person, the average US citizen, and compared to the rest of the people in this lab. Then after going over the sheet, the water resources sheet, we're going briefly covering again human population growth and touching upon what we learned last week about exponential growth equation or the exponential growth model. We're going to be going over the exponential growth equation and then looking at the different variables within that. And then you're going to be practicing using that equation in your breakout rooms and doing part A on the lab 4 assignment. And afterwards, we're going over the ecological footprint. What is it? Global patterns, looking at the US, looking at other countries. And then you're going to be looking at your own ecological footprint and doing part B of this assignment that's due today. So first, if we wanted to look at, well, the deliverables for today, that's due before next class that we meet, so next week, you're going to be turning in the lab 4 responses. This is that Word doc that's on Canvas. So part A, exponential growth, where you're doing some equations, and then part B, where you're looking at your ecological footprint. I will show you where to find that when I also go over the water use chart. So, but by next week, you're also going to upload your water use chart, which is 7 days or 1 week's worth of data. And then you're going to fill it out and then upload it to Canvas before we meet. So first, for the personal water use data collection, you're going to download a copy of that from Canvas. It's under the Lab 4 link. And then you're recording your personal water use for 7 days. You're completing this data sheet by filling in the totals for the week. And then, uploading it before we meet next week, prior to the beginning of lab, because we are going to be using that data, putting that data into a Google Sheet to make some graphs. So where you can find that is if you go into lab 4, under the first couple of links on the lab 4 page in Canvas, there is like the intro background information where you can take the pre-lab quiz, and then there's the water use data sheet, which you can download, and you can just click on here to download it. And then also for today, we are going to be going over the lab 4 assignment questions here. So when you click on the lab 4 assignment questions, that should download as a Word doc where you can answer some questions later. But this is where you can find your water use data sheet to go over what that would look like when we do when you do start filling it out. It's going to look like this, blank. So how you can fill it out is first, as an example, there you can put your name at the top, the types of the residence type that you're in, either dorm or an apartment or a house or a shared apartment, something like that. And there are different water use activities that you're going to be recording. So it could be a bath, shower, flushing, like the number of flushes for your toilet. If you're looking at brushing your teeth, it's like how many minutes do you run your water. So say if we're looking at baths, you don't take like a full bath until like day 3, so you can like cross out the other days and just tally up one. But for your showers, you would record that in minutes, and you would write those down as, say, 7 minutes, day 1, 5 minutes, day 2, and on, and tally that up at the end, where under total events, you would just add that all up, the entire week worth of whatever tally or however many minutes, and you would multiply that by the gallons per unit for that water use activity. Because every, how much water you use for your bath or how much water you use when you wash your dishes is going to be different. So you would multiply that by the gallons per unit for that activity. And the units, or some of the examples, have 2 different numbers. And that's because the second number, with the asterisk, is for low flow devices. And low flow devices are basically if it's been replaced within your lifetime, like by the time that you've been alive, it's a low flow device. If it's older than you, just a general rule of thumb, if it's older than you, then it's probably not a low flow device, and you can multiply it by that top number here. So after you multiply your total events by your gallons per unit, that's going to equal your total gallons consumed. And you would add all of that up to get your estimated, or your total number of gallons used in 1 week. So that's the amount of water that you use within that 1 week. You're going to make a hypothesis. So say my water use will be higher than my class's average because I did a lot of laundry, or maybe I cooked a lot and I washed a lot of dishes more than usual, or something like that. So you would write your hypothesis at the bottom here. But that is basically it for the water use sheet. Did anybody have any questions about that? No? Okay. Awesome. So now moving on to population growth. Human population growth, more specifically, which ties into what we were going over last week about different population growths of wolves and moose, and we saw how they affect each other. But now we're going to look more specifically at ourselves, at humans. So as a review from Lab 3, we are going over this video that you can find on the Lab 4 Canvas page 2, where it's going to go over more specifically exponential growth and what would that look like in terms of an equation. But let me just share that really fast too. And okay, so it's an hour long, but we're just watching the first 8 minutes. And let me just play that for you all here. Okay, this is this professor from the University of Colorado, a physics professor that goes over more specifically the exponential growth equation. And I think it's really helpful in terms of explaining in depth a little bit more that. So.
Well, it's a real pleasure to be here and to have a chance just to meet with you and talk about some of the problems that we're facing. Now, some of these problems are local, some are national, some are global, but they're all tied together. They're tied together with arithmetic, and the arithmetic isn't very difficult. And what I hope to do is I hope to be able to convince you that the greatest shortcoming of the human race is our inability to understand the exponential function. So you say, well, what's the exponential function? This is a mathematical function that you would write down if you're going to describe the size of anything that was growing steadily. If you had something growing 5% per year, you'd write the exponential function to show how large that growing quantity was year after year. And so we're talking about a situation where the time that's required for the growing quantity to increase by a fixed fraction is a constant. 5% per year, the 5% is a fixed fraction, the per year is a fixed length of time. Now that's what we want to talk about, it's ordinary, steady growth. Well, if it takes a fixed length of time to grow 5%, it follows it takes a longer fixed length of time to grow 100%. Now that longer time is called a doubling time. We need to know how you calculate the doubling time, and it's easy. You just take the number 70, divide it by the percent growth per unit time, and that gives you the doubling time. So our example of 5% per year, you divide the 5 into 70, you find that growing quantity will double in size every 14 years. Well, you might ask, where did the 70 come from? The answer is it's approximately 100 multiplied by the natural logarithm of 2. If you wanted the time to triple, you'd use the natural logarithm of 3. So it's all very logical. But you don't have to remember where it came from if you'll just remember 70. Now, I wish we could get every person to make this mental calculation every time we see a percent growth rate of anything in a news story. For example, if you saw a story that said things have been growing 7% per year for several recent years, you wouldn't bat an eyelash. But when you see a headline that says crime has doubled in a decade, you say, my heavens, what's happening? Well, what is happening? 7% growth per year. Divide the 7 into 70, the doubling time is 10 years. But notice, if you're going to write a headline, you never write crime growing 7% per year, because most people wouldn't know what it really means. Now, do you know what 7% really means? Let's take another example from Colorado. The cost of an all-day lift ticket to ski at Vail has been growing about 7% per year ever since Vail first opened in 1963, and at that time you paid $5 for an all-day lift ticket. Now, what's the doubling time for 7% growth? 10 years. So what was the cost 10 years later in 1973? 10 years later in 1983? 10 years later in 1993? And what do we have to look forward to? Now, this is what 7% means. Most people don't have a clue. Well, let's look at a generic graph of something that's growing steadily. After one doubling time, the growing quantity is up to twice its initial size. 2 doubling times, it's up to 4 times its initial size. Then it goes to 8, 16, 32, 64, 128, 256, 512. In just 10 doubling times, it's 1,000 times larger than when it started. And you can see, if you tried to make a graph of that on ordinary graph paper, the graph will go right through the ceiling. Now let me give you an example to show the enormous numbers you get with just a modest number of doublings. Legend has it that the game of chess was invented by a mathematician who worked for a king. The king was very pleased. He said, I want to reward you. And the mathematician said, my needs are modest. Please take my new chessboard and on the first square place 1 grain of wheat. On the next square double the 1 to make 2. On the next square double the 2 to make 4. Just keep doubling till you've doubled for every square. That will be an adequate payment. Well, we can guess the king thought, this foolish man. I was ready to give him a real reward. All he asked for is just a few grains of wheat. Well, let's see what's involved in this. We note there are 8 grains on the 4th square. Now, I can get this number 8 by multiplying 3 2's together. It's 2 times 2 times 2. It's 1 2 less than the number of the square. Now, that follows in each case. So on the last square, I'd find the number of grains by multiplying 63 2's together. Now let's look at the way the totals build up. When we have 1 grain on the first square, the total on the board is 1. We add 2 grains, that makes a total 3. We put on 4 grains, now the total is 7. 7 is a grain less than 8. It's a grain less than 3 2's multiplied together. 15 is a grain less than 4 2's multiplied together. Well, that continues in each case. So when we're done, the total number of grains will be 1 grain less than the number I get multiplying 64 2's together. And my question is, how much wheat is that? You know, would that be a nice pile here in the studio? Would it fill the building? Would it cover the county to a depth of 2 meters? How much wheat are we talking about? The answer is it's roughly 400 times the 1990 worldwide harvest of wheat. Now that could be more wheat than humans have harvested in the entire history of the earth. And you say, how'd you get such a big number? Well, it was simple. We just started with 1 grain, but we let the number grow steadily till it had doubled a mere 63 times. There's something else that's very important. The growth in any doubling time is greater than the total of all of the preceding growth. For example, when we put 8 grains on the 4th square, the 8 is larger than the total of 7 that were already there. When we put 32 grains on the 6 square, the 32 is larger than the total of 31 that were already there. Every time the growing quantity doubles, it takes more than all that you'd used in all of the preceding growth. Now, let's translate that into the energy crisis. Here's an ad from the year 1975, and it asks the question, could America run out of electricity? America depends on electricity. Our need for electricity actually doubles every 10 or 12 years. That's an accurate reflection of a very long history of steady growth of the electric industry in this country, growth at a rate of around 7% per year, which goes with doubling every 10 years. Now, with all that history of growth, they expected the growth would just go on forever. Fortunately, it stopped. Not because anyone understood the arithmetic, it stopped for other reasons. But let's ask, what if? Suppose the growth had continued, then we would see here the thing that we just saw on the chessboard. In the 10 years following the appearance of this ad, in that decade, the amount of electrical energy that we would have consumed in this country would have been greater than the total of all of the electrical energy we had ever consumed in the entire preceding history of the steady growth of that industry in this country. Now, did you realize that anything as completely acceptable as 7% growth per year could give such an incredible consequence that in just 10 years you'd use more than the total of all that had been used in all of preceding history? Well, that's exactly what President Carter was referring to in his famous speech on energy. One of his statements was this. He said, and in each of those decades, more oil was consumed than in all of mankind's previous history. Now, by itself, that's a stunning statement. Now you can understand it. The president was telling us a simple consequence of the arithmetic of 7% growth each year in world oil consumption, and that was the historic figure up until the 1970s.
So that was just a really good intro back into how we can look at exponential growth in a different way through this specific type of equation that we saw, which is the, which I will go over actually right now. So if we're going back to cover what we looked at from lab 3, we went over exponential growth, that growth model depicting unlimited growth where there's unlimited resources, food, water, space, and no predators and such, which produce that J-shaped curve. So we know that that doesn't define reality, and we know that a more realistic model to look at would be the logistic growth model that takes into account the environment's carrying capacity. So our carrying capacity, which is limited by these variables such as again, like the limits to resources that we'd have. So, and the presence of predators and external changes like climate change. And when the carrying capacity is taken into consideration, that's when we get that S-sigmoidal shape where it starts to curve and slow down near the carrying capacity, that K, and that changes according to all these different variables too. But going on to refer to what that video showed us, it briefly went over more, like it went over exponential growth, and it also went over this exponential growth equation, which we are going to be using for part A for this lab. So the exponential growth equation, it's written differently than how we saw it last lab. It's just in a different notation though. It still takes into consideration the same variables. So we have n is equal to n naught times e to the kt. So our n is our population at that time. So whatever population we have at this certain point in time is equal to n naught, which is the initial population size at time 0, multiplied by e, which is the inverse of natural log. So it's this constant value that you can plug in. It's a button on your computer, on your on your calculator. And that's just like what you can just type in for e to the kt. So k is the annual exponential growth rate, not the carrying capacity. K in this equation is just our exponential growth rate that we're looking at for this case study, whatever case study, times the time, which is however much the time period that we're looking at for whatever problem. So as an example, if we were going to be looking at exponential growth and say we are trying to estimate future population sizes, say we want to look at the global population in 2030, we would be looking for N. So what would that be? Say right now our N naught, our population in 2010, we're given 6.07 times 10 to the 9 people as our initial population at 2010. Our E is our inverse of natural log. We can find that right on our scientific calculator, which is it's going to be the inverse of ln. Or you can find it on your graphing calculator, and that is the inverse of ln here. So there's also online calculators that we can use, but that is where you can find the inverse of natural log. I will be going over some online calculators that if you don't have a scientific or graphing calculator, that's where you can use it. But then our K, if we're given our annual exponential growth rate of 1.25% per year, we could rewrite that as a decimal as 0.0125 for our K. And for our time, since we're trying to estimate the global population at 2030, and we're using what we know from our N naught from 2010, we're looking at our 20 years, that's our time period for our T. So taking into consideration all of this, how can we find our N? So we're given this equation, and all we have to do basically is just plug in what we know. So we know that our N naught, our initial population size is 6.07 times 10 to the 9. We'll plug that in. It'll be, we'll multiply that by our E function. So we'll just write in E to the K, our growth rate. So our 0.0125 or 1.25% multiplied by T, our 20 years. So we can plug that all in. If you don't have a scientific or graphing calculator, you can use Desmos. So Desmos Scientific, if you go and type that in to Google, it would look like this. And we're given, so when you type in Desmos, it's going to look like this, Desmos / scientific. And say we have so it's, sorry, one moment. If you wanted to type it into Desmos, it would look something like this. So say we have our parentheses is really important when we're trying to find or use or try to find or do any calculations, especially if there's anything to the exponent of. So I'm gonna put my 6.07 times 10 to the 9. And we'll end our parentheses, and we'll multiply that by E. And our E we can find in, there's different tabs on the side here, so you can put in ABC or different functions. So we'll multiply this by the different functions which we can find on the side here for E. And going back to our main setup, we're also going to just put in that remaining our K times to the our growth rate multiplied by our T, our time. So we're going to go to the exponent of, again, we'll put in parentheses, our growth rate 0.0125. We'll end our parentheses and we'll multiply that by 20, which is our time. And we're given our answer here. So now we know that it's estimated in the year 2030, there's probably going to be 7.79 times 10 to the 9 people. And that would be how we could use Desmos, the online calculator, and the same process of putting in your equations and using parentheses. That would be the same process for either the graphing or scientific calculators if you have it handy near you. But if not, this is how you can use the online one. So back to the PowerPoint. That's how we can use this equation as is. But there's also other ways we can solve for other variables within this equation. So say if we're trying to find the exponential growth rate, this is just the equation that we saw from the last slide, but rearranged where we're now looking for k, our growth rate. So if we just rearrange the entire equation, this is how we can plug in all of these variables to find our k. So say that none of the values really changed. We found that in the last slide that our population at year 2030 is 7.79 times 10 to the 9 people. We can plug that into our n at the top. Our initial population size, it's still 6.07 times 10 to the 9 people. We'll plug that in for our n naught. And then E is our constant value. We're not changing that, but now it's going to be natural log because E is our inverse of a natural log. So instead of E, we're using natural log when we're using this equation for K. And again, T, our time period that we're looking at is 20 years. So if we plug all of this in, we're given K is equal to ln, and in parentheses, we have our n, our population at 2030, 7.79 times 10 to the 9, divided by our n naught, our initial population size, 6.07 times 10 to the 9. And we'll end our parentheses, and that's our entire top portion of our fraction. And we're going to divide that by 20, our time period. And when we plug all of this in, we'll be given our final k as 0.01247. And if we round that up and just put this as percent, it was that 1.25% that we were using before. So this equation is just another way of finding different variables for us. So yeah, so that's one way we can find your exponential growth rate. Let's say we're trying to now try to find a different variable, which is our time. If we had all of these other variables, but we just don't know the time period between when we had our initial population to our current population, we can rearrange the equation again to where now, if we're trying to find T is equal to ln, in parentheses, our n, our population size, over n naught, our initial population size, n parentheses, divided by k, which is our growth rate. So again, our variables are basically the same, but now we're looking for T, where n is equal to 7.79 times 10 to the 9 people, and not our initial population size is 6.07 times 10 to the 9 people. E again is that button on our calculator, a constant value, and our K we know is 1.25%, or rewritten as a decimal is 0.0125. So in the equation, if we're going to plug in all of the variables, it would look like this. So we have our T is equal to ln, we have our n naught, or our n, our population size, divided by our n naught, n parentheses, and then everything divided by our k of 0.0125. And if we plug all of this in, we would get our T is equal to around 19.96 years. And we can round up from here and we can say it's around 20 years, which we can confirm from knowing from our basic setup that it was looking at our initial population size at 2010 to our future population size at 2030. And that was our 20-year period. So this is another equation that when you rewrite it, you can find our T, this variable. But now, if we're looking at doubling time, say we have a population that doubles from our n naught, our initial population, to our current population size, there is a simpler way of doing, of finding our doubling time or our time. So when we can do that, say we have around 2.00 times 10 to the 9 people as our current population size, and our initial N naught is 1.00 times 10 to the 9 people. Again, our E is a constant value and our K is 1.25%. Rewritten as a decimal is 0.0125. So you can see from our N naught to our N, it just doubles, and where our 1.00 times 10 to the 9 just doubles to get our 2.00 times 10 to the 9. If we plug that into our T, our doubling the time equation, that divided by our 2.00 times 10 to the 9 divided by 1.00 times 10 to the 9. When you divide that, you're going to be given 2. So that top portion of our fraction is just going to be ln 2 all over our k, our 0.0125. And say if we went through plugging it into our calculator, ln of 2 is 0.693 and on, divided by our k. And say if we're going to get rid of that fraction, or like if we're going to put our k back into like a decimal, we would multiply this our fraction by 100 over 100, and we're given 70 over 1.25, and we know that 1.25 is our k, and that would just be our final function, where if we're looking at doubling anything, any population doubling in time, we can just use this equation where T is equal to 70 over K. So the original time equation still works if you want to use it whenever you see a population doubling in size, but I think it's a lot easier if you just use this T equals 70 over K, because then it just takes out all this extra math that you don't really have to do. So with that, using this final equation, we find that in this situation, the doubling time is, or the time it takes for our population to double is 56 years. So now let me go over a little bit about population growth and human population growth. There's pretty interesting websites out there that show the growth of different populations in different countries, and that's what I can show you all right now. So if we go back to these websites are also available in this PowerPoint that's attached on Canvas. So if you wanted to look at this later and play around, you can too. So for our population clock, this website, it's based off of the US Census Bureau, and see, when we click right into it, it's our world population clock. It's pretty interesting because we can see that the population of the US, how is it growing? How is it slowing down, the different variables that take into consideration. So some components that affect our population in the US is that we see around every 9 seconds, one birth is happening. Around every 11 seconds, someone's passing away. And we also have international migrants around every 666 seconds. And so that means every 40 seconds, we would gain one person to our population clock. Yeah, and on the right side, we can see the world population. Well, right now we're at 7.7 billion people and growing. So the 10 most populous countries as of July 1st, 2020 is China, India, US, Indonesia, Pakistan, Nigeria, Brazil, Bangladesh, Russia, and Mexico. So it's just really interesting to see like the dynamics within the world, especially later on as we consider developing and developed countries and what does that mean for them, for the world and resource consumption when we have like the most, just taking into consideration like the population sizes of different countries and how much resources do they use. So you can see at the US right now, this is as of July 1st, 2020, this was our population size. Since it's been updated as of today, March 3rd, 2021, you can see that it's grown over time. But if we scroll down, we can also just get a better idea of the distribution of our population within the US. So we have our Southwest, Midwest, and Northeast on this graph on our right, and we can even tell the United States population by age and sex on our right graph. Sorry, the left graph is the population growth by region. So on our right, as of 2019, we can even scroll and see that, say around in your 20s, in the US, around 0.67% of people in the US are male when they're 20, and around 0.64% of the people in the US in their 20s are female. And it's just pretty interesting to see this dynamics between different age and sex. But if we scroll down too, we can also see the different population sizes of different states too, of the most populous and the most high density states. So the most populous right now at the very top is actually California, where in California, we have around 39 million people. And as of 2019, and per square mile in 2019 was around 253.5 people. So that's pretty interesting, I think, to see like the distribution within like specifically the US. You can play around, and I think you can look at more specifically like the different world, like the different countries within the world in this link. But we can also, this website, it's referring to the US Census Bureau and what is counted on the US Census Bureau. So, but it could be more accurate. So if we, the second link that we can find on the slide is the human population clock, where this is using equations and calculations like JavaScript 3.0 to calculate our human population within like the world. So this is made by a professor at UC Berkeley, and it's we saw that there was the population clock before. This one just takes in consideration a little bit more specifically at this point in time, what is the human population? And you can go back in time or forward into the future. So did anybody want to share like a specific date that they wanted to look at this point? I know before in other classes, they would want to look up their birth dates or something like that, but yeah, if not, I like to go to May 1st, 1999. This is the date that the first SpongeBob episode was aired. And right now we can see, as of today, there is 7.5 billion people in the world. But at May 1st, 1999, there was around 5.9 billion people. So 5.9 billion people to today, that's like around like 1.6 billion people that's been added on since the first SpongeBob episode was aired, and it's a lot. It's a lot of people. Yeah. So if you wanted to like play around and find your own birthday within this time, or like what was the human population when time you were born, or at this certain point in time, this is like one of the human population like equations or websites that you can use. Now, let me go back to our PowerPoint. And so we saw that human population, it's on the rise, it's growing exponentially too. So this is due to artificial inflation of carrying capacity. So this really refers to resource availability based on technological advancements. What that really means is that we have been borrowing resources from the future by the technology that we use that kind of give us more resources than we currently have. If we think about our agricultural industry, where we have the technology that goes into our agriculture, where it's just getting better and better over time, where we can produce resources, farm animals at this rate, and also grow food at a rate that hasn't been done before. This is due to maybe the use of pesticides or herbicides or fertilizers, or just the way that we farm our food. So it's just the amount of resources that's available to us now has grown a lot. So our population in turn has also grown by a lot. But the damage that herbicides, pesticides, and fertilizers do to our soils and to our agricultural land, it's not sustainable. You can't really continue farming and doing agriculture the way that we do for long periods of time, because it is damaging to the soil and the just the surrounding environment, and it has implications for like the environment that you're doing agriculture on. So our carrying capacity, even though we've made it a lot larger because we've grown our carrying capacity where we can support more humans, because we've created more resources through advancing our technology, eventually we are going to reach our carrying capacity, our new carrying capacity, and that's going to affect us in different ways. So with our current resource usage, we're going to see some changes moving forward, and if we're not seeing them now. From here, we are actually going to look at doing the equations that I've gone over in this slide. So I would suggest going on to lab 4. Oh, sorry. If we go into the lab 4 Canvas page and say, if we click into the lab 4 Canvas page, when you download the lab 4 assignment questions, so it's going to look like this. One moment. It's going to look like this. So you're just going to be doing part A for this next 20 minutes. I'm going to put you in breakout rooms, and using the equations that we went over, you're going to look at exponential growth in terms of what would it look like in the stock market. And then with that, you're going to go and look at human history moving forward, and then using the different equations, look for annual growth rate. Given the annual growth rate, you're looking at the time that it would take for a population to grow up. So for question 3, you would be using your doubling time equation, because your population, your N naught of 5 times 10 to the 9 people, it doubled when it got up to 10 times 10 to the 9 people. And what I would suggest is opening up the slides, the slide 4, lab 4 slide presentation that you can find on Canvas, and then having those equations next to your Word doc and referring to those equations as you do these problems. Again, Desmos is, if you don't have a scientific calculator or graphing calculator anywhere near you right now, you can use Desmos, this online calculator. And if you are comfortable using Google or Word doc, you can just type in your equations by clicking into wherever you want to start, and you can insert equations. So right next to the Home tab, there's this Insert tab. And all the way at the end of the toolbar, you can insert your equation. And when you click on Insert Equation, this little box is going to pop up. But if you're not comfortable using equations, the equation function in Word doc, you can just write out all of your work on a piece of paper, and then take a picture of your work and then submit it on Canvas like that. So you can either put your work, do your work on your Word doc by typing it in, or you can just write it on a piece of paper off to the side and then submit it that way. So for part A, you'll be doing these 5 questions within your group. I'll be popping in and out to see how you're all doing, but besides that, did you all have any questions moving forward? No? Okay. Okay, awesome. So I'll be putting you all in breakout rooms and save for the next 20 minutes. Maybe like we'll give you 23 minutes and we'll meet at 9:40. Okay, so let me just put you on breakout rooms. I will see you all at 9:40. So we just went to our breakout room. So now we're going to look more specifically at our ecological footprints, at our own resources that we use. So what is an ecological footprint, or EF? So this estimates how much biologically productive land area is needed to support the resource consumption of one individual. So per person, how much productive land do you need to support that person? So it's measured in global hectares, GHA. 1 hectare is around 10,000 square meters, or that's around 2.5 football fields. So it's that's how we can look at global hectares. And some background on the average US citizen's ecological footprint is around 7 GHAs, or global hectares. While when we're comparing it to the average human worldwide, their ecological footprint, it would be 1.7 global hectares. And we're just going to be looking at some more trends about how is this resource distribution, how does it look between different countries and per person too. But these numbers are based off of a Global Footprint Network's 2015 study, and it's changed over time, and it's been different in the past too. So now if we're going to be looking at more specifically ecological footprints of the world, worldwide, on this chart, there we have our world map in different colors. The darker shade of red, the more hectares or more, the higher their ecological footprint is per person in that area. So we can see in Northern America, it's like the darkest red, one of the darkest reds around. So again, this is looking at hectares or global hectares or ecological footprint per person. And we can see that the distribution overall, we can see that highly developed countries are more, per person, they have a higher ecological footprint. So more specifically now, if we're going to look at highly developed countries, so this graph is looking at 2010 data of ecological footprint per country per capita. So on our horizontal axis, there's our different countries listed out from highly developed and moving onwards based off of ecological footprints. So on our Y is the per capita ecological footprint per person. So each person estimated, like it's a average in that company that each person would have this ecological footprint, like this amount. Our key is to look at the different parts that their ecological footprint, what is it made up of? Is it gray, carbon, yellow for cropland, light green for grazing products, dark green for forest products, light blue for fishing grounds, or orange for built up land. So if we're looking at developing countries or highly developed countries, say if we're looking at the United States. The United States here, for our ecological footprint, we see that it's mostly carbon. There's a lot of carbon, which makes sense because we have where we use a lot of fossil fuels in both the energy that we need to power things and also by the types of cars and our transportation sector and what that looks like for us. But we also see that there is in part yellow, so some cropland per person used to produce the food that we eat, and grazing products, fishing products, all of that. But mostly we see that a big chunk of our carbon or ecological footprint is taken up by carbon released. So that's from the fossil fuels in our energy industry. But moving on now, if we're looking, this is our highly developed countries. Our ecological footprint per person is pretty high. But now looking at developing countries, so the in green, this line is our world average biocapacity per person, which was basically if you the average ecological footprint worldwide, it would be this at this point. So this is for the average person around the world. And we see that for developing countries, it's a lot lower, their ecological footprint, and their carbon footprint is a lot lower because many different reasons, but probably because they use less fossil fuels in their transportation industry, and they are more reliant on croplands and on food production, and that's what makes up most of their ecological footprint. So the differences between both, we can see that it's pretty big. So moving forward, if we're going to look at between at ecological footprint by region over time, we have our 1961 graph at the top and our 2010 graph at the bottom. So this is looking at the average ecological footprint per capita in population across different regions. So we're looking at different countries over time. We have North America in our dark pink, EU in purple, other European countries in green, Latin America in dark blue, Middle East in light blue, Asia Pacific in pink, and Africa in this orange yellow. So on our graphs, we have our populations in billions on our X, our horizontal axis, our vertical, our Y-axis is their ecological footprint per capita per person. So right now, in 1961, we saw that the global population was around almost exactly 3 billion people. And if we're looking at that point, the global ecological footprint, the average was around 3.2 global hectares. But at this point too, we can see if we're looking specifically at North America, there's a lot less than 500 million people in North America, but their ecological footprint is a lot higher than all of the other countries too, where it's almost around 7 global hectares per capita per person. So moving forward in time, if we're looking at 2010, we see that it hasn't really changed that much. Again, we're taking, like for Northern America, still less than 500 million people, but they're now getting closer to that 7 global hectares per capita per person. So the resource consumption for North America has gone up, but compared to the rest of the world, the population size, has grown, but not much. So there's still a small amount of people using a lot of resources within North America, but compared to 1961, when we had around 3 billion people, in 2010, we had a little bit less than 7 billion. It's now past 7 billion. As of today, it's like 7.5, depending on which like population clock you look at. It's past 7 billion people worldwide now. But you can see that even though there's more people like today, the resource consumption is still, it varies a lot by different countries, but if anything, it's definitely grown for each country over time. So like going over more of ecological footprint by national per capita income, looking at low income countries, middle income countries, or in high income countries, we, on our graph, on our horizontal, our x-axis, we have time from around 1960s to 2003. And on our y-axis, we have our global hectares per person, which is our ecological footprint. And in our different colored lines, we have our low income country in green, middle income country in blue, and high income countries in red. So over time, we see our low income countries, it's pretty stable. There's not low income countries, their ecological footprint, the amount of resources that they take up, it hasn't really grown all that much. Middle income countries, we see that there was some growth around certain points in time, and there was some late points in time where their resource consumption also decreased, but generally it's also pretty stable. But now if we're looking at high income countries in red, there is a steady amount of growth over time. And there are some decreases in resource consumption at certain points in time, but overall, steady increase where more and more from 1961 to 2003. On this graph, we can see that there's pretty steady income increase in resource consumption. And that has implications for the people who don't have access to this resource, or the world that we live in, and where are we getting these resources from too. So the goal is to, well, looking at this graph, the human development and ecological footprint, this is from the UN, using the UN Inequality Adjusted Human Development Index. So availability of resources and where certain countries are getting their resources from and the distribution of that, it has implications on the world overall. So across our X, our horizontal axis, is our UN Inequality Index, where we're going from low human development to highly developed, very high human development. So our very high developed countries to our developing countries. And on our Y is our ecological footprint per capita. So per person, how, like, what is their average, what is their what is their ecological footprint at this point? So we have our different countries in our color codes in our keys. So the goal is to be in this green square at the bottom, where you are both very highly developed as a country, but your ecological footprint is also below at this sustainable amount. So you can see the bigger the circles are, the more people are in that country at that point. And there is a lot of people in developing countries where they're still working on, where they're still developing, and their ecological footprint in turn are also low. But there's also, we're looking at North America again, which aligns with the other graphs that we looked at, where we have, they're very highly developed, but also takes in a lot of resources, and their per capita ecological footprint is pretty high too. So the goal is to be both highly developed and be at the sustainable ecological footprint. But right now, that at one point there was one country who met both of those standards, and that was Chile. But that is no longer the case. I think that was around 2003 or 2010. But yeah, this is our goal, to be both highly developed and to be sustainable per person. So now we're going to be looking, we just saw global ecological footprints, and we're looking at our own ecological footprint by taking our footprint quiz. I'm putting you in breakout rooms to take this quiz, but if we click on this link, which is the footprintnetwork.org, it would look like this. So Oh, sorry. If we are looking at lab 4, if you click on that link, you can just also type in footprintnetwork.org, and it would show you this website. So on the Global Footprint Network, this website, there's a little bit of background information, measure what you treasure, and all of that. There's data that it's available to us, but what we really want to do is on the left side is to calculate our own ecological footprint. And if we just click into calculate now, it'll take us to our footprint. So on this quiz, it's going to measure different resources that you take up, and our Earth Overshoot Day 2020 is August 22. What that means is that by the time that this year started, looking at everyone that lives on Earth, using the amount of resources that we use, how much, when is the day that we've used more than one Earth's resource? And now we're looking at how many Earths is going to take to sustain yourself. So if we click on to take the first step, it'll take us to through different sections where we're looking at the at different parts of our own life and how would that change our final footprint. So we would say for this first question, how often do you eat animal-based products? For me, I would say often, so a few times a week. And then, but you can also improve your accuracy of your quiz by clicking on add details to improve accuracy. And say for beef and lambs, once every few weeks, I don't really eat beef or lamb. Pork, you can adjust and say every few weeks. Poultry, so like chicken, nearly every day. Fish or shellfish, maybe often, and then such and such. So you can just save your results. And that's how you can improve your accuracy of your quiz. If we are going back to the Word doc, it'll just go over what you're going to be looking at for part B. So in part B, there's that footprint link to the quiz if you're not there yet. That's where you can find the quiz that you're going to be taking. And you're going to be taking this quiz twice. So one is for your USF residents, your San Francisco residents here, and then one is for your childhood home. If they're the same, if you grew up in San Francisco and you are also living in the same house that you're now going to school in, you can just take the quiz once. If you have only ever been doing online Zoom classes throughout your going to USF, you can also just take this quiz once. Just type it into your Word doc and just tell me that that's the case, and then just do that quiz for your one residence. But you're going to take this footprint quiz twice, and then at the end of that quiz, there's it's going to tell you how many Earths you take up for the lifestyle that you lead, and then you're going to just take a screenshot of that and then paste that into your Word doc, and just write a few questions discussing your results, and also just talk within your breakout room and just compare to your table, your breakout room. What is there something different between each of your guys' ecological footprint? And could it maybe is it because I eat more meat? Is it because I drive more, or things like that? So that is what you're going to be doing for part B. I'm giving you another 20 minutes for that. Did anybody have any questions before we go into our breakout rooms? Okay. All right, so another 20 minutes, that's going to be 10:20. I'll be popping in and out to check on your progress and answer any questions. But if you're all good with that, I guess I'll see you all at 10:20. Hello. As people are coming back from their breakout rooms, I hope everything for part B has went well, that you got a chance to finish your second quiz and then talk amongst your breakout room, amongst your people there to just compare and contrast. But did anybody have any questions on that, or it seems like everything's been pretty okay with that part? Okay, awesome. So more towards that second session, say, let me share this part. Let me share the talk with you. So for part B, we have these questions at the bottom where how accurate is this analysis? Well, it's as accurate as you make it to be. Really, like you can improve your accuracy by improving like the details for each section and just answering it to the best of your ability that you know. But also, if you think about question 6, what are some assumptions that go into this analysis? We're assuming that every single car uses the same amount of gas. We're assuming that jet fuel burns the same way, or that every chicken that you eat has the same ecological footprint too. So if you're thinking about chicken, there's even from factory farm to or just like a regular farmed chicken, those footprints between the type of meat that you eat, they're going to be different. So assumptions that go into that, you can talk about some examples like that. Question 7, how do scores vary among your table? Again, I hope you had a chance to talk to everyone in your group about what, if it did, was it any different? Was it lower? Was it higher? Why? Things like that. You can talk about what are factors that are most likely to be influential in your final footprint score. Maybe you eat more meat. Maybe you drive a little bit more. Maybe even flying once or twice a year makes a huge difference in your ecological footprint. So question 9, how might you lower your ecological footprint without compromising your lifestyle? You can talk about more about, the same factors that you think influences your final footprint score, and how could you affect those factors? Could maybe changing like changing around some parts of your commute, or thinking about the different types of resources that you use, maybe consuming less meat, different types of meat, because beef versus chicken, very different ecological footprints. But let me also stop sharing. And let's go back to the PowerPoint.
Sorry, Maggie, can you explain again what it means by what are some assumptions that go into the analysis?
Sure. So assumptions, more specifically, we're just thinking about each type of resource that we use. So if we're thinking about food, we're assuming that the type of food that that there's the same footprint, like specifically if we're thinking about like chicken versus beef, or chicken, the type of chicken that we eat. So even though we're assuming that we can be specific by saying that we only eat this much chicken within a week, there's different footprints with how that chicken is grown. So factory farm chicken, where you massively produce and just grow and just farm a lot of chicken in one place, is very resource intensive, and it also creates like a lot of waste and has different effects on the environment, versus if you're eating chicken from like a more locally grown farm, those like footprints change and they're different. Also, the fuel that you use for your car, that's going to make a difference on the amount of carbon that you put out and things like that. So there are assumptions that that everything is the same for everyone, but it's not really. Yeah.
Thank you.
Yeah, of course, no problem. Okay, and I think in the chat, Kyle attached the climate clock metronome, where basically a clock was put up, I think, somewhere. And it was basically counting down how much time do we have left before climate change is starting to like really make an effect on our population. And honestly, populations and these predictions, as climate change is happening, the different effects like disasters and hazards, they're just increasing and magnifying over time. So it's happening more often, and they're just getting more damaging too. That we're seeing them now, like especially with floods and like earthquakes and such. And it's happening. And if anything, predictions never really show the full extent of what it could be like. So right now, there's always been plans to address climate change and make changes to, like, I guess, reverse the effects of climate change. And we've even known since the beginning of the 1900s, there was history where they look at global warming, climate change, about increasing temperatures over time and what that would mean for our environment and the world that we live in and the resources that we use. But it's not like there's always been plans that are published within the government that really good intentions behind it, but there's always like not consistent actions that go into implementing them or pushing through different actions within the plan. Or it's just overall, even within different levels of government right now. I'm from Hawaii, so I'm looking at like the different resilience plans in Hawaii, and within even Hawaii, between the local government and the federal government, their resilience plan over time, they're either not updated or they are updated, but they're not, there's just not like the actions behind it or the efforts behind it kind of fizzle out over time. And we don't really track the progress on what really works for resilience for a coastal community. And there is, just not consistent effort to really push through actions. But I think more and more over time, people are acknowledging that climate change is an issue. So that's really nice. And if anything now, there's not, in the past, it's always like, is climate change real? Are these effects really happening? It's not really a question now. I think right now, more focus is on what can we do to change where we're going and, kind of help with our situation where we are. And I think that's really nice, especially with our new administration. We just recently joined the Paris Agreement again, where all the other countries in the world, they were originally joined in, and now we can really start working on our Green New Deal. So this plan, in the middle of our previous administration, there were people in our government that were a little bit just like a little bit disheartened by where we're going. So they even made like specific plans about, so if this happened, if we had a change in administration, what would we need? Who would need to do what? And how can we make the changes that we need to do? So our Green New Deal and all of these plans are put into action. And there's very specific steps that going forward would help, I think, especially with, the amount of resources that we use. So there's a lot of hope, actually, I think, moving forward. But some background information. I think I can talk like a long time about this. So I think I'm just gonna go back to our PowerPoint and just share just final things about today's lab. So now, deliverables. So before next class, you're going to turn in to Canvas Lab 4 your responses. So part A, your exponential growth, the calculations that you did for part A, and then part B, your ecological footprint. So your quiz results for that, and then answering those questions at the end, like maybe a couple of sentences for each question. And you're also going to upload your water use chart, where starting today, you're recording the amount of water that you use for the next week, for the next 7 days. And after you fill that out, you're just going to turn that into Canvas. So instead of a pre-lab quiz, you're going to be filling out this chart. And again, this is what this chart looks like. If you go into Canvas, say if we go back into Canvas, under lab 4, this is where we can find our, can you see this screen, Canvas? Okay, okay, it'll be like this link. When you click into it and download it, it's going to look like what I showed you on this slide. And then after, so after you fill it out, you're just gonna turn it in before you meet for lab next week. And we're gonna be making some charts and looking and comparing within our own class. So going back, that is basically what you have to turn in. There is no pre-lab quiz again. You're just gonna be filling in this chart. And if there is no other questions, I will see you all next week. And I hope you have a good rest of your day.
Thank you.
Thank
Thank
you.
you.
Thank you.
Thank
Have
you.
a good day.
You too. Thank you.
Professor,
Yeah.
I have a quick question.
Sure.
So what, I kind of missed this. I think you went over it, but